So last lesson, we looked at this schematic diagram here, and what this shows is a single slit here, monochromatic source on one side, single slit. The waves, of course, diffract through that single slit like so. And hopefully strike this surface such that slit 1 and slit 2 each receive a wave at exactly the same time. Hence that wave, of course, diffracts through there and diffracts through there. And as a result, they interfere with each other. And we see an interference pattern on the screen over here. I showed here that at this point here, so if I highlight in blue this line to P2, what does P2 show? I'll actually draw this line. Sorry. What's happening at P2? Can anybody say? What's that, Matthew? Bright fringe. There's a bright fringe. Which bright fringe? It's the and I was hoping that you'd know this delta y is the distance between what and what. Yeah, that's right. Or the first minimum and the second minimum, or the third minimum and the fourth minimum, or the fourth maximum and the fifth maximum. It's the distance between fringes, essentially. And if I go from P0, which is the central bright band, delta y, how far have I, to which bright band have I moved? It's the first order maximum, isn't it? It's the first bright band. First bright band or fringe P2. And anybody tell me the path difference here between the distance from S1 to P2 and S2 to P2? So I've got to draw another line here. I've drawn from the center there. There. Is one what? It's one wavelength, isn't it? Yes, you're right. Yeah. So the path difference, which of course is this line segment here, S2D, and remember this diagram is not to scale. S2D is very small. It's of the order of one wavelength. One wavelength for a light, visible light, of course, is of the order of 10 to the power of -7 meters. Okay. So very, very small path difference. The path difference at that point, d sine theta equals 1 lambda, or just lambda. Okay, for P2. We went through the proof. I don't like the proof, but we went through the proof all the same. And then we looked at the fringe separation and how we do calculations for the fringe separation. I'll note also, I've said the path difference is equal to d sine theta. And another way to write that is d sine theta, path difference, is equal to m lambda, where m is some multiple of the wavelength. It could be 1, 2, 3, 4, or the calculations that we're going to do, it could be 0.5, 1.5, 2.5, 3.5. And one thing I wanted to make certain you understood also is that the distance to P2 from P0 is exactly the same as the distance from P2 on this side to P0. This bright fringe, or this point, we're calling this point 2, is the first bright fringe, is the same distance on the other side of the central maximum as this bright fringe here. A problem for you. Young's double slit interferometer. Remember what this device looks like. You may use one. Here it is here. Is illuminated with red light of wavelength 670 nanometers. So on this side of the interferometer, because you're on this side here looking through the eyepiece, on this side we've got red light of wavelength 670 nanometers. We talked also yesterday about the fact that, I think we talked about the day before the fact that it's very hard to get one wavelength, very specific wavelength. In fact, we're usually getting a range of wavelengths that are very, very close together. A narrow band of wavelengths, you would say. But never exact. It's too hard with the apparatus that we have available to us. You could use filters. You could use a laser. Laser has a frequency at best with a range of 100 hertz, which isn't bad. We're going to look at LEDs as well. So LEDs, we're going to give you a range of colors of LEDs to look at. The double slits are 0.15 millimeters apart and the screen is 30 centimeters away from the double slits. Find the angular position of the second minimum on the screen. Now, I like to put this picture up when I'm talking about second minimums and first maximums. This is a good one. Just take that part of it. What are we talking about when we talk about the second minimum? Well, there's the central maximum. Let's go down this time. First minimum, that's the center of the first minimum. First maximum, second minimum. That's the center of the second minimum there. At 0.3, what they're saying is P3 there. Okay, so how many wavelengths out of phase will the two slits be? Will be the light from the two slits at this point here. 1.5 lambda, isn't it? Thank you. One wavelength there, 1.5, 2, 2.5, 3, 3.5, etc. And so I'll just give you some information. Most people would get this right. 670 nanometers. How do we write that? Yeah, we do. I mean, in scientific notation. Oh yeah, okay, we can change. 670 by 10 to the minus 9 meters is 670 nanometers. Double slits are 0.15 millimeters apart. 0.15 is 1.5 by 10 to the minus 4 meters apart. And 30 centimeters is 0.3 meters. 1.5 lambda. You could say 1.5 lambda, or what they do in the book, 3/2 lambda. Yeah. Have a go at this, please. So D sine Theta equals m lambda. Theta, now angular position theta, sine to the power of -1. Sine to the power of -1, m lambda, so that's m lambda on d, isn't it? M's 3 on 2. 1.5 times 670 times 10 to the -9 over 1.5 times 10 to the -4. Theta equals, we got 0.384 degrees. Nobody's throwing their hand in the air. Have a go at the force maximum. Has anyone done this already? Question 2. That was 1. So knowing for both of them, I'm just going to repeat what I said before. Theta, or the angular position, is the same for both interference patterns. D is the same for both. So we have d sine theta equals fourth bright fringe, 4 lambda, and d sine theta equals sixth dark fringe. Let's have a look at our picture. Well, it's hard to see because there's one dark fringe that's lambda on 2, 1.5. So there's 0.5, 1.5, 2.5, 3.5, 4.5. The sixth dark fringe would be 5.5 lambda. 5.5 is 11 on 2, your text says. So knowing that d sine theta and d sine theta equals are the same, 4 lambda, 1, actually that's lambda 1, isn't it? And that's lambda 2. 4 lambda 1 is equal to 11 on 2, lambda 2. We know what lambda 1 is. If I leave lambda 2 by itself, lambda 2 is equal to 8 over 11 lambda 1. 8 on 11 times 580 by 10 to the minus 9. We get lambda 2 is approximately equal to, now remember, I should have been doing this earlier, 422 nanometers. This approximation for wavelength, remember that our source is not necessarily completely monochromatic. Our calculations, d sine theta equals m lambda, is not perfect because we're not talking about 90 degrees, we're talking about 89 degrees and things like that when we do the proof for d sine theta equals m lambda. So you need to remember that. I don't think they would take marks if you just said lambda 2 equals 422 nanometers. I just want you to remember that it is an approximation. Very close to, but it's not exact. Another problem. The problems in this portion of the text come thick and fast, which is good. Monochromatic light from a fine single slit illuminates 2 narrow parallel slits. Whoops. The centers of the 2 slits are 0.6 millimeters apart. An interference pattern forms on a screen 40 centimeters away. The fringe separation on the screen is 0.424 millimeters. Find the wavelength of the light. This is a typical question from your practical, the practical that you will do. Have a go, please. Let's get our values correct. Centers of the 2 slits, so D equals 0.6 millimeters. which is 6 by 10 to the minus 4 meters. Is that right? Interference pattern forms on a screen 40 centimeters away. So L equals 0.4 meters. Fringe separation, delta Y, is equal to 0.424 millimeters. 4.24 by 10 to the minus 4 meters. We know this. The fringe separation is equal to the wavelength multiplied by the distance between the slits in the screen divided by the distance between the two slits. Lambda from that is equal to thank you, delta Y D over L. Then it's not so hard, yeah, 4.24 by 10 to the minus 4 multiplied by D, which is 6 by 10 to the minus 4 all over L 0.4, and we get approximately equal to 6.36 by 10 to the minus 7 meters, which is 636 nanometers. Approximately. Who got that one? 6 people, 7 people, 8 people, good. 8 out of 26 isn't bad. Last example for now. Laser light illuminates 2 narrow parallel slits, and the interference pattern produced is observed on a wall 5 meters away. The distance between the two slits is 0.3 millimeters, and the angular position of the fifth maximum is 0.5 degrees. Find the wavelength of the light. This is another situation you might be encountered with during your practical exercise. Okay, L equals 5 meters. M equals 5, fifth maximum. D equals 0.300 millimeters, which equals 3 by 10 to the minus 4 meters. And theta equals 0.5. .50 degrees. D sine theta equals m lambda. Is that going to solve our problem? There's lambda, we know m, we know theta, and we know d. Lambda equals d sine theta. On m. Done. These are too easy for you. 3 by 10 to the minus 4 times sine of 0.5 all over 5, and you should have got, correct me if I'm wrong, 5.24 by 10 to the minus 7. No. Yeah. approximately 524 nanometers. Who got that one? Pretty much. What? Oh, okay. Here's the situation. Any questions there? Excellent. You might have seen we can determine the wavelength of monochromatic light by making measurements of the two-slit setup apparatus. Okay, so you need to know D. D. The distance between the slits. L. The distance between the slits and the screen. And you need to know this. The fringe separation. Yeah, well, actually, you don't need to. If you, or if you, either this or the angular spread of the fringes. Yes, theta, or theta, angular position. Okay. Uh, you could set this up, given a laser. We're almost there. I'm going to shine a laser across the room. Could be in here. It'll be a helium neon laser. And what setup? I have a laser, which I think is, which I'll consider coherent laser light. Can anybody see straight away what I could do over here in order to find the wavelength of that light? What if I put a wall Okay, I could put a wall over here. What have I put here? Yes. What sort of slits? Two slits, okay. So let's very narrow two slits. Okay. What's going to happen is the laser light, the coherent light, goes through those two slits. That's what? Uh, so picky. Okay. There you go. There you go. All right. Happy? Yeah. Now, what's going to happen as it passes through here? Well, you're going to get this sort of thing happening, aren't you? They're going to interfere with each other. And what are you going to see on the wall over here? Hands, aren't you? So we're going to essentially see this happening. You could say you might see that, you might see that, and you might see some more angular spread as well. Okay. Now what do we see what we need to know here? All we need to know is D here, the distance between the two slits. And then we can measure this, either theta or the fringe separation. And we can find lambda, the wavelength of that monochromatic light. Okay. If I have one more thing, if I have this is what I see. What's the best way, please people, what's the best way to measure the fringe separation, do you think? If it was that size, hypothetically. How would you measure delta y? What's the best way, the most accurate way to measure delta y in this situation? Oh, yeah, okay, so you could say, all right, well, I'm going to take the center of that band to the center of that band, and I'm going to measure between the two. You could do that. Measure that distance there. There's another way to get more accurate, become more accurate. And do what with it? But then you have to know the scale of your picture and all that sort of stuff. Oh, yeah, okay. Put a ruler next to it and take a picture. Or you could just read the ruler while you're holding it up there. No, there's another way. It's not that hard. Yes. No. What am I always telling you to do when you draw your graphs and you calculate your you're calculating the gradient of your graph. When somebody does this, when somebody calculates the gradient of their graph like that, yeah, that's no good, is it? Why is that no good? You want to take your gradient like that, don't you? Yeah, that's right. Yeah, exactly. So what if I did this? Instead of just taking between two, I took as far as I could. Because we know they're all the same distance, don't we? And so I could measure from there to there. The fringe separation is the same across the board. I could measure that, at what distance that was, and I could say that's 1, 2, 3, 4, 5, 6, 7, 8, 9 divided by 9. I get the fringe spacing more accurately. Okay? To measure the fringe spacing, use as many as possible. And divide by the number of fringes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Hang on. 1, 2. Yeah, hang on. Divide by the number of spaces. The Young's double slit interferometer, I've said this already. I'll just repeat it one more time. You see crosshairs. They look something like this when you look through the eyepiece. And essentially you just move them across and count how far the micrometer moves. That's not easy. It's not easy to do. We might stop there today. It's Friday.